Okay, we're coming to the end of chapter 3 here, 3.4, and today we're going to introduce an object that's absolutely fundamental to calculus. It will make up the bulk of our study for the next several weeks. It is the derivative. And just to really quickly recap what we did last time, section 3.3, rates of change, we have a function y equals f of x. Here I've gone into the point x equals a, and I've drawn in the red tangent line to this curve at x equals a. Right? And we defined last time the instantaneous rate of change of f of x at x equals a. Think of that as the slope of the function. Well, the slope of the function right here is just the slope of the tangent line. Right? So the instantaneous rate of change of the function is the slope of the tangent line. And we had talked about how to define this, right? We had slopes of secant lines, and we pushed 2 points together, and we said, well, the slope of that tangent is just going to be this expression, the limit as h goes to 0, of f of a plus h minus f of a over h. Okay, so that tells me the slope of the tangent line at x equals a. And we went through some examples where we said, okay, here's a function, let's find the rate of change at x equals 2 or x equals 3 or whatever. But you'll notice that a is sort of whatever you want it to be, right? You choose a. So you can think of a as being variable over here. Well, if a is variable, why not let it actually be variable, right? Why not choose a letter that we usually use for variables like x? And if I'm allowed to plug in any old value for a, then I actually have a function, right? I plug in a value and I get out a number. So that defines a function. So since a is variable, let's actually make it a variable. Let's actually make it a variable. And this will be our definition. Right, this is the definition of the derivative. It's, I'll write something here in just a second, but it's just that expression. It's the limit as h goes to 0 of f of x plus h minus f of x over h. Right, so you decide x. You plug in a value for x, and you evaluate this expression, and you get out a number. That is a function. So we're going to give this function a name. What people usually denote it as is f prime of x. Okay, so I start off with this original function f of x, and I'm defining f prime of x. This is called the derivative. The derivative of f of x. Why the derivative? I suppose perhaps because I'm starting with the function f of x and I'm deriving from it a new function. It's f prime of x. I'll show you how this works in just a second with some examples, but this is perhaps one of the most important definitions in calculus. That is the definition of the derivative, right? So you start off with a function f, you evaluate this expression, this limit, and you output a brand new function that we tend to call f prime. This is how this is usually read, f with an apostrophe, so f prime of x. That's called the derivative, and think about what this is doing, right? It's just this guy. What did that thing do for me? That expression gave me the slope of the tangent line in x equals a. Well, this gives me the slope of the tangent line at any value x that you specify. Alright, so if you want to know the rate of change at x equals 2, you evaluate this expression, and then you find f prime of 2. Or if you want to find the derivative of 3, or the slope at 3, you find the derivative, f prime of x, and then you plug in x equals 3. Right? So the derivative f prime of x tells us the slope, right, the rate of change. It tells us the slope of the original function f of x at the point x that you choose. So the derivative of a function tells us something important geometrically about the original function. It tells us the rate of change of the original function. So we'll do an example. I'll make this more clear with an example. Okay, so so far we just had a bunch of theory, but this should feel more concrete now when we go through this example. So find the derivative f prime of x for f of x equals, we'll just do a simple polynomial, x squared minus x. Okay, so how do I find the derivative? Well, I use my definition, f prime of x. It's the limit as h goes to 0 of f of x plus h minus f of x all over h. We've been working with limits like this for quite a while. I, of course, can't just plug in h equals 0 straight away because I divide by 0. I'm going to have to do some work here. But let's figure out what these expressions actually are. So for us, f of x plus h, everywhere I see x, I plug in x plus h. So we're looking at, I'll rewrite this because I need it here. Limit as h goes to 0 of x plus h all squared. I plug in x plus h for x minus x plus h. I'll put that in brackets just to indicate that's the first piece. And then minus f of x, x squared minus x. Being careful here to put this stuff in brackets so that this negative distributes over the whole thing. And then all divided by h. So we'll keep going. Let's see, I'm clearly going to want to FOIL this out, so let's expand this really quickly. Here I've got x squared plus xh plus xh, so plus 2xh plus h squared minus x minus h. And now we'll distribute this negative, so minus x squared minus minus x is plus x all over h. And I suspect a whole bunch of stuff cancels, so let's figure out what we can cancel here. X squared minus x squared, those go away. We've got a minus x and a plus x, those go away. And as I had hoped happened, everything left has an h common to it, so I'm going to factor out an h right now. This is h times 2x plus, pulling out an h from here is plus h. And here, pulling out an h from this expression leaves me with minus 1. Right? So minus 1 all over h. Now we've finally fixed our problem. This h that caused us to divide by 0, it is gone. It factors and cancels with this h. So we have a limit as h goes to 0 of a much simpler expression, just 2x plus h minus 1. And what does that do? Well, now plugging in h equals 0 is no problem, right? I don't divide by 0 or anything like that. So as h goes to 0, well, this just goes to 2x plus 0 minus 1. Or 2x minus 1. Alright, so I'm going to erase this, but I want to recap really quickly what we've done. So we found the derivative. We found f of x was 2x minus 1. Again, hence the name derivative, right? I start with a function, and from that function I derive a new one. I derive this brand new function. I start with x squared minus x. I derive from it this brand new function, 2x minus 1. And it tells me something geometrically. This function tells me the slope of f of x. The derivative tells me the slope of f of x at any value x you want. Right, so if I wanted the instantaneous rate of change of f of x at 2, I would find f prime of 2. And this is the, let me call it the slope. Slope of f of x at x equals 2 is f prime of 2. And that's just 2 times 2 minus 1, 2 times 2 minus 1 is 3. If I want the slope of f of x at, you choose any value, x equals negative 10, well that's f prime of minus 10. And it tells me the slope of the original function at minus 10. So that's 2 times minus 10 minus 1, that looks like minus 21. And so on. You can plug in any value x that you want. What's the big advantage here? The big advantage here is back in the last section, 3.3, if someone said, find the instantaneous rate of change of a function at, I'd say 2, you would go ahead and you'd evaluate the limit with a equals 2, right? And then they say, okay, now find it at minus 10, you'd evaluate the limit at minus 10. Then they give you another number, you'd evaluate that limit at that new value. Here, the big advantage is, once I've computed the derivative one time, right, I've got this function, now it's very, very easy to find the slope at any point that I want, at all. Right, so this is why derivatives are so nice. It saves us a lot of work by just coming up with one function to give us the slope at any point that you want. We'll do one more here. Find f prime of x if f of x is the square root of x plus 2. Alright, so once again, I want f prime of x. I have to know the formula for it. It's the limit as h goes to 0 of f of x plus h minus f of x over h. And as long as you know that much, now it's a question of how good am I at evaluating limits. So we'll see what we can do. Limit as h goes to 0, f of x plus h, that'll be the square root of, replace x with x plus h, so square root of x plus h plus 2. I put this in brackets for no real reason, just to indicate that's the x. Minus the square root of x plus 2 all over h. Now, as always, I'd like to somehow factor an h at the top to cancel this thing down here so I don't divide by 0 anymore. How do I do that? Well, I see square roots. I see these radicals, and if I have a radical, a plus or minus something else, I'm thinking let's do this rationalization technique. All right, so we'll multiply top and bottom by the conjugate of this expression. And because I'm going to run out of space, how about I just do it all up here in one line? So the conjugate of the top is just make this minus a plus, so square root of x plus h plus 2 plus the square root of x plus 2 divided by the same expression. And as long as I multiply and divide by the same thing, I haven't changed the function. It's like multiplying by 1. Alright, so what do we have? Again, I'm not going to be lazy. I need this limit here. Try to keep this in your work as you go through. Don't drop the limit, right? It really needs to be there. So what do we have? Up top, again, this is a difference of two squares factorization. So if you FOIL it out, you just get that difference of two squares. So it's this term squared, which is x plus h plus 2, minus this term squared, minus x plus 2. Once again, making sure to use brackets to distribute this negative over the entire expression. All over h times a bunch of stuff. X plus h plus 2 plus the square root of x plus 2. So what cancels? X minus x, 2 minus 2. And what do I have up top here? Because this is a video, I'm just going to modify this. What do I have up top? I have just h. Right, after doing that cancellation, I have just h up top. Well, if I have just h up top, that's h times 1. And h is multiplying everything on the bottom. So this becomes 1 over this expression. What happens now? I suppose maybe I'll rewrite it one more time. Limit as h goes to 0 of 1 over the square root of x plus h plus 2 plus the square root of x plus 2. So you'll notice h going to 0 is not a problem anymore, right? It's not. I'm not dividing by 0. Nothing bad happens when h goes to 0, so just let h be 0. And what do I have? I've got the square root of x plus 2. Sorry about the handwriting here. Square root of x plus 0 plus 2, so square root of x plus 2. Square root of x plus 2 plus the square root of x plus 2. And we're done, but it's written in sort of an ugly form. Square root of x plus 2, square root of x plus 2. I have two of them. Just add them together. That's 1 over 2 times the square root of x plus 2. and there's our derivative. I said there's one other type of function we could take the derivative of using limits and so on using this technique. It's functions that look like 1 over x. I won't do it in the interest of time, but the textbook does a perfect example just like that. It's a function like 3 over x or something. Alright, so just to recap, we start with a function f, and we build this brand new function, f prime of x, called the derivative of x, or the derivative of f, right? So we build this function, and it tells us geometrically, it tells us the slope, right? The value, you plug in a value for x into the derivative, the value that you get out is the slope of the original function f at that point x. But derivatives are defined in terms of limits, right? And limits don't always have to exist. As we've seen, limits don't always exist. And that means derivatives don't always exist. The good news is you can sort of classify geometrically when they don't exist. You can see, if I give you a function f of x, you can see when its derivative isn't going to exist. So I'll tell you all 3 ways right now. Here's the classic case. One is, I'll even give you a function that demonstrates this property. It's y equals the absolute value of x. Alright, so for positive values of x, it looks like y equals x. But for negative values of x, well, absolute value of x would be minus x. Alright, so looks like that. Alright, so here's the function y equals the absolute value of x, and the derivative doesn't exist right here at 0. Derivative does not exist at x equals 0. Right, why not? Well, if I came into any of these points, right, if I came into any of these positive values of x, you'd easily be able to tell me the slope. The slope is actually exactly equal to 1, right? And for negative values of x, you'd be able to look at this and say the slope is negative 1. But what about right here, at this corner? Right, what happens at the corner? If I try to put a tangent line on it, should it be horizontal? Should it slope like that or like that? And the answer is you just don't really know, because as you come in from this direction, the slope is minus 1. Coming from this direction, the slope is positive 1. Actually, at this kink, or this corner right here, what happens? And the answer is the slope is undefined. Right, so if the slope is undefined, then the derivative can't exist, because the derivative outputs the slope. And there is no slope right here. Right, so this is an example of, number 1 is something like a sharp corner. If you see a function with a sharp corner at a point, then you know its derivative isn't going to be defined there. Sharp corners aren't in practice really going to happen too often though. 2, this can happen fairly regularly, but it's also not going to happen super often. Again, I can give you a function that demonstrates this property. It's y equals the cube root of x. Alright, so if I were to try to graph this function, it looks a bit like this. Yeah, close enough. This is roughly the graph of y equals the cube root of x. Once again, right here at 0, the derivative is undefined. Derivative does not exist at x equals 0. Why not right here? Well, if you tried to measure the slope, again, if I tried to measure the slope at all these points, it's defined. It's just the slope of the tangent line. But what about right here at x equals 0? Well, it gets steeper and steeper and steeper and steeper, and if I put down a tangent line right here, you'd have to say that tangent line looks like that. Right? Instantaneously, this function is sloping completely vertically. Right? It's right here at 0, it's completely vertical. What's the slope of a vertical line? Well, infinity, but infinity is not a number, so the slope of a vertical line is undefined, which means the slope of this function, the rate of change right here at 0, it's undefined. And if the slope is undefined, that means the derivative can't exist, because the derivative tells us the slope. So this would be an example of something like a vertical tangent line. Again, in practice, it doesn't happen all that often, but as you've seen, just this very simple function, y equals the cube root of x, demonstrates this behavior. So it can happen. And number 3, is just any old discontinuous function. So here's a function that comes along, it's got a hole in it, it goes on, it makes it jump, then it blows up to infinity, then it comes back. Alright, so here's our function. And what I'm trying to draw here is this is discontinuous. And at any points of discontinuity of a function, your derivative automatically doesn't exist. Okay, so I've got these 3 discontinuities right here. I've got this hole, sometimes called a removable discontinuity. We've got this jump discontinuity here, and here we've got this infinity thing, this infinite discontinuity. Derivatives do not exist at discontinuities. Not the nicest looking arrows in the world, but that's okay. Alright, so there's 3 ways derivatives can fail to exist. Maybe I should have gone in a slightly different order. 1 is if you're discontinuous at a point, your derivative automatically doesn't exist there. 2, the second sort of prototypical case that people think about is these sharp corners, having kinks in your graph. If you have a sharp corner, the slope there doesn't make any sense, so your derivative is undefined. And last but not least, this vertical line stuff can happen. If your function instantaneously goes vertical, it has infinite slope, well that means the derivative isn't defined, because the slope isn't defined. So derivatives are very, very, very important. Make sure you understand how to find them using this limit definition, and make sure you understand what they do. Right? Try to forget about, we went through rates of change, we defined the rate of change at a is the limit as h goes to 0 of f of a plus h minus f of a over h. Well, in truth, you'll never use that expression ever again. Right? If you want to know the rate of change at a, you just find the derivative, and then plug in x equals a. Right? So understand what the derivative is, what it's used for, and we will spend the next several weeks studying derivatives in even more detail. Right? We'll build up what we know about derivatives and what we can do with them. Thanks.